Hey guys, thanks for coming out to my talk. I'm going to be talking about breaking detection with X86 ISA specific malware. My name is Chris Hernandez. It's my Twitter handle. I'm the Red Team program manager at Code42. Former sysadmin, pen tester, and built a few Red Team programs. A company in the US called Target. And before that, I was a consultant at the Varus Group Adaptive Threat Division. That group has done some offensive PowerShell development that you guys might be familiar with. But for today's agenda, what we're going to be talking about is the state of detection, malware detection in the enterprise, the state of AV evasion, or what adversaries typically try to do to hide their payloads. And we'll go into a high-level overview of the X86 ISA and go through some thought process, hypotheses, and testing, and then finally we'll have a few proof of concept videos. So before I get started, I wanted to acknowledge a few researchers who've done really interesting work on sort of like similarly themed topics. So Josh Pitts and Travis Morrow have done some really interesting work on genetic malware or like keyed malware. And then Christopher Domas has done a lot of really interesting work just on X86 in general. And this talk tries to kind of combine both of those tracks. And then one of the quotes that kind of got me thinking about actually presenting this research is from Matt Graber, and he said, as an offensive researcher, if you can dream it, someone has likely already done it, and that person isn't the kind of person who speaks at security cons. So here I am talking at a security con. So sort of the genesis for this idea was really I wanted to ask the question, can I make sure that my malware or my agent runs on my target and not other places to the best that I can control? And what can I do to ensure that this doesn't take place in code? Because if your malware sample gets caught by any sort of detective capability, right, eventually it's going to get to a reverse engineer, and really no malware can sustain the the work of a group of trained reverse engineers for long enough. But as somebody who does adversary emulation, my job is to really make their job as hard as possible so that I can persist and have access as long as possible in order to achieve my objectives. So this is kind of what the state of malware detection looks like in most enterprises, or most enterprises that care about security. We'll do things like block suspicious or malicious domains, check DNS. We'll block suspicious or unusual emails and attachments with some sort of mail security appliance. We block untrusted code with either app whitelisting or blacklisting or certificate validation. We might block malicious code with machine learning or signatures or magic pixie dust, whatever the newest trend is in the detection space. Hopefully we're scanning and ingesting all of the unusual traffic that we see in our environment. So whether that's files crossing the wire, or unusual files on an endpoint. So for example, there's a number of next-gen AV solutions that if you drop a binary to disk and that binary has not been seen by that software before, they immediately grab the binary and ship it back to their sandboxes for their own analysis. And then presumably, your organization might be subscribing to some threat intel feeds, looking at IOCs, and then searching for those particular IOCs in your environment, pivoting on that and trying to find bad stuff. So at a high level, the state of malware detection in the enterprise kind of looks like this. The bottom level of the pyramid is just an alert gets generated. And something about that alert is interesting to a triage analyst or your entry-level analyst in your SOC. And our job as red teamers or as adversaries is to either make our payload look as normal as possible, try to hide the evil that we're doing, or if that isn't possible, make their job of understanding our payload as difficult as possible. So in this case, our goal is if an alert is generated, we want that alert to get passed to a triage analyst. We want the triage analyst to not be able to understand what's happening. And we want them to escalate that to a more senior analyst or a reverse engineer. All of those steps are going to be buying us adversaries a little bit more time in your environment. So that's on the detection side. What does the offensive side typically look like? So things you've probably seen before are some of your payload or some of your payload stages being encrypted, along with anti-debugging techniques, anti-VM techniques, obfuscation, and environmental keying, or that's that genetic malware that Josh Pitts had presented on. And my thought was that all of these things are currently deployed in code. And yes, it's a computer, so you can never fully get away from code, right? Ultimately, it has to execute at some point. And my thought was, what if the code that I'm trying to execute is allowed to execute on my target systems or specific target systems that I'm interested in, and due to some form of hardware incompatibility, it's not able to be executed on things like the sandbox, or even better, the reverse engineer system. So in order to set up this testing environment, there's a few things that we had to think about. And that is that the X86 instruction set is not a static instruction set. You've probably heard that it's a CISC architecture, meaning it's complex, and more and more opcodes or registers or features can be added. It's also a fact that if you have a newer X86 CPU, it might be capable of doing something that older systems are not capable of doing. And that's actually taking place in hardware. Like if there's new registers or new instructions, specifically registers, those things wouldn't exist on the older CPUs. And so the other thing to consider is there's probably no environment that anyone uses that's a monolith, meaning everyone has the exact same computer on workstations and servers and in the cloud. So typically we have different CPUs, and as a result, different ISA features on our desktops versus our servers versus what we're using in the cloud. Some of that we can control, and some of it we can't. So as I mentioned before, X86 is a complex instruction set. Over time, there's more and more opcodes that get added to the instruction set. Some can even be taken away. There's lots of undocumented instructions. And then there's some really old research on 32-bit malware and legitimate binaries that was done in 2006, and where roughly 90% of all the opcodes present in the binaries that were tested was accounted for by 14 opcodes. So the majority of X86 instructions, while there's hundreds of actual opcodes available, there's very few that typically get executed in your average executable file format. So as I was doing the research, I realized that there's a lot of similarities between what we're doing here and keyed malware, right? But I think the key difference is that for keyed malware, you're deriving the key from something in the operating system or something that is part of maybe the network or the domain or a driver. And typically, you'll read that key and then use that key to decrypt your second stage payload. Here, I would call something like this maybe ISA keyed malware, because what we're doing is we never read a value from the system, such that a reverse engineer wouldn't be able to see, like, oh, this binary is, like, say for example, reading the domain name and using that as the key to try to decrypt this stub. So if I supply the right domain name, I'm supplying the right key. In this case, a reverse engineer would have to supply the right CPU. So there's definitely ways to work around any of these techniques. However, it's a little bit more complicated to go find the correct hardware than like patch a binary, again, in software. So historically, what we've seen is that Intel has added new registers and new opcodes or instruction sets with every major release of CPUs. And what I thought when I started doing this was that each CPU was going to iterate exactly on top of the next one, meaning like every CPU that comes out today will be backwards compatible with all of the prior instruction sets. And when I was looking into it, that actually wasn't the case. So if you think of our CPU fabricators as software developers, they're trying new things. Instead of in code, they're fabricating CPUs. And some of those things don't work, and so they go a different direction, much like a developer would. So here we can see in the early Westmere Xeon processors, they added support for 128-bit registers and enhanced SSE instructions. And then the Xeon E5 family added support for the AVX instruction set and 256-bit registers. The next generation after that added additional AVX instructions, still at 256-bit registers. And then something interesting happens in the middle. There's the Xeon Phi coprocessor. And Intel came out with this. It had support for 512-bit registers. However, it had no backwards compatibility with any of the previous instruction sets. And then at some point, Intel realized that that wasn't really a good idea, so they sort of abandoned that architecture. And in the second generation of the Xeon Phi processor, they changed that, and they went back to backwards compatibility as well as adding AVX 512 instructions. And on the last column, the important thing to note is that they added some AVX 512 instruction sets from the previous Xeon Phi processor, not all of them, and then they added new ones. So in the recent years, there's quite a variety in the types of opcodes that your processor could actually support. As a result, there's a ton of different registers that exist on your CPU. And I realize that this slide is pretty small, but on the right-hand side are all the registers that you might be familiar with, like the instruction pointer, stack pointer, base pointer, all those kinds of things. However, on the left-hand side, those are all the things that we're interested in using for ISA-specific malware, because those are the potentially missing registers in certain CPUs. So on the right-hand side, the blue column are the 128-bit registers. Purple column is 256-bit registers. And the final pink column is the 512-bit registers. So there's actually a lot of registers that have been added. And as somebody who hasn't done a lot of assembly programming, that was pretty interesting to me. So now we need to move into testing our hypothesis. So in my environment, our testing sandbox was running an older Xeon E5 processor. So opcodes that we might want to test would be 256-bit or 512-bit opcodes, and using either of those size of registers as well. But first, we've got to do some baselining. So we're going to generate some like standard vanilla x86 malware and see how our sandboxes score it. And then we're going to see if we can enumerate the hardware on certain sandboxes without having access to it. Of course, our test sandbox we do have access to, but as a red teamer or adversaries potentially won't have access to your sandbox, so they need to figure out a way to get that data out of the sandbox. So again, our basic test case with generic like x86 and x64 opcodes. It was a interpreter Linux reverse shell. We uploaded it to a couple different sandboxes in VirusTotal, and it was scored appropriately. So out of 100 being completely bad, it scored a 91, or ranked malicious, and then 11 out of roughly 60 AV engines detected the file. No surprise there, right? It's an interpreter. Second test case was the same thing, only for Windows. And it actually scored worse, even though it's essentially the same thing, different operating system. And because it's a Windows binary, we had support for more sandboxes uploaded to all the sandboxes, and it was appropriately scored as being really bad stuff. So, we ran into the problem of, again, we could test our own sandbox and intuitively know what type of hardware it's running, but how can we get that information from other people's sandboxes? There's a really easy way. Some of the sandboxes will generate a report for you. Certainly the free sandboxes will, and they'll take screenshots. So in this case, we uploaded a payload that just popped up the CPU ID, the CPU version, and the specific ISA instructions that are supported. So the font is really small. It was taken out of a report, but on the left-hand side, there's a commercial sandbox that is running a Xeon E5 processor. And the interesting part is on the left-hand side, it's, I believe, is a Intel Core 2 CPU, which is pretty old, is a free sandbox, and I'm not sure if they're just like running it on donated hardware, or you can't, if it's actually running in a VM, certain VMs allow you to like patch the response back from the CPU ID instruction. That might be possible, but there's still ways that we can really understand and figure out what CPU is actually running on the system, whether or not it reports it as such. So what if you don't have access to your report? One option is to create a payload that, again, runs the CPU ID instruction. Base64 encodes that value and then creates a web request and connects back to your web server, makes a GET request for the base64 encoded value, and then you just decode that, and it's the string of your processor. Another one would be any sort of sandbox that makes a report on what DNS or what HTTP requests your payload makes. Then the CPU string is the base64 encoded URL in the network communication section of the report. So we made this sort of proof of concept payload and sent it to VirusTotal to see what we could get back. And these were our results. The number of sandboxes that executed our malware was a pretty good amount, and for the most part, they were roughly running the Intel Core processor. We didn't deduplicate it, so I think actually that bottom column is the same sandbox running it multiple times. But if we were looking at making malware that could generally run on most systems and avoid detection in most sandboxes, I would again target something like the AVX 256 instruction set or AVX 512, because there was only 2 Xeon CPUs in the results that could possibly execute those opcodes. So now we need to Now that we've gotten our hardware information out of sandboxes, we need to create our proof of concept and get hopefully a shell. And to do that, I took the reverse shell payload and compiled it with the Visual Studio compiler, adding AVX 512 support. And so this is an example of the payload running in a system that doesn't support the AVX 512 instruction set. So it's Core i9 desktop processor. And we see that double-click on the payload, it just crashes. We'll go into our debugger, look at the instructions, and see that I set a breakpoint right before the AVX 512 instructions where what we're dereferencing a value and putting it into an AVX 512 register. Because the CPU physically doesn't have an AVX 512 register, it just throws an exception. And so now what does it look like when we have support for those instruction sets? Here we're running on a Xeon Platinum system in AWS. And for good measure, we're running our Windows Defender. And double-click on the file, and we immediately get a shell back. So we're administrator, and we can see that we have access to files in the local file system. So as intended, the payload is running on the system that we want it to, but not running on the systems that we are trying to avoid. So in order to see how this would work in the real world, we took our AVX 512 compiled payload and uploaded it to all the sandboxes that we could find. And there was really no good analysis or detection on it. We did get information that analysis failed or that there was an exception. 2 engines scored it as malicious, although I'm not really sure why. I hadn't heard of those AV engines before, so they might score everything pretty aggressively. So what are the detection options that you have? If you run your own sandbox in your environment and you detonate a payload in Cuckoo Sandbox, for example, you'll record that an exception was caught. It'll be a null exception address and a hex 5 exception code. So you could potentially look for that. If you are using a cloud-based sandbox, you could potentially download any faulting or failing samples for your own analysis. And I think the important thing to take away from this, or that we took away from it, is that any code that executes in your sandbox but fails doesn't necessarily mean that the binary was bad. We need to go and investigate why those payloads failed or why those binaries failed, and not just assume that there's not an issue there. So future research for me, Intel is sort of branching out into a lot of really different ways. One of the interesting things is they have some CPUs with embedded FPGAs. So again, you could potentially do some really weird stuff where on a traditional X86 processor, you have access to an embedded FPGA, and then they're doing a bunch of other stuff. Additionally, I thought there would be ways to combine the leaking data from the sandbox piece with delivering the appropriate payload. So you ask the CPU, like, what version of the X86 ISA are you? And then your second stage payload would ship it the most appropriate ISA version payload for it. So we got 1 minute left. Does anybody have questions?